Hello everyone, and welcome back. Today we're going to be continuing our exploration of differential equations and take a brief look at some of the basic things that you definitely should know when analyzing higher order ordinary differential equations. So let's just quickly go over some of the equations that we have been talking about before in terms of first order differential equations. So a first order differential equation is one that can be represented in the form y prime is equal to some arbitrary algebraic function of x and y. So some special examples of first order differential equations that we have discussed instantly are equations of the form like y prime plus axy is equal to b of x, which is our general form for first order inhomogeneous differential equations. We also have equations of the form like y prime plus axy is equal to b of x times y to the power of m, which is an example of a nonlinear first order equation, which some people also refer to as a Bernoulli equation. And you could also write some first order differential equations in the form mxy dx plus nxy dy, where m and n are some arbitrary functions of x and y, which is usually the representation that we would analyze to sort of see if that equation is in exact or non-exact form. Right, and there's infinitely many other variations, but those are the three of the most common ones. So what we're going to do now is we're going to increase the order to second and higher. So some examples of differential equations that you'll see eventually are x squared times the second derivative of y with respect to x plus x times y prime plus x squared minus alpha squared, alpha some constant times y, is equal to 0. Another example would be m y prime, m a constant, plus c y prime, c a constant, plus ky k a constant, is equal to some algebraic function of x. And there's obviously many other variations as well, but these are two special ones that we will eventually discuss. So the natural question is, well, how do we solve higher order differential equations? Right? Obviously, it's going to be generally more difficult, but let's start off with a nice example that actually we can solve without having to learn any new tricks. So the first type of higher order differential equation that we're going to explore is what is called the reduction of order approach. And this can be used if y double prime and y prime is present in our differential equation, but the expression y is not present in that particular expression. So for example, let's look at one of these, y double prime plus 5 over x y prime is equal to 3 divided by x squared. So notice that this is going to be a second order differential equation. We have our y double prime here and some other stuff elsewhere. But notice that there's no y term here. So we'll just have y double prime and y prime. So sort of how this is going to go is we're going to create a new function. Let's call it, for example, u, and we're going to let u be equal to y prime. Because if u is equal to y prime, then u prime is going to be equal to y double prime. Okay, let's also introduce some initial conditions so we can get an exact solution. In particular, we're going to have y of 1 is equal to, let's assume it's 1 over 32. Let's assume y prime of 1 is going to be equal to 1. Okay, so those are going to be my initial conditions. We're not going to use those until the very end, but let's just mention them now just as a start. So using these newly defined functions u and u prime, now I can rewrite my differential equation in the following form. So u prime is just another way of saying y double prime, so we can say that this is going to be equal to u prime, and over here we're going to have 5 over x times u, and that's going to be equal to 3 divided by x squared. And we already know that this is going to be a first order linear inhomogeneous differential equation, so we know we can solve this with integrating factors and separability via integration. Okay, so what is going to be our integrating factor? So since the function in front of u prime is going to be 1, our integrating factor is going to be the exponential of the integral of that function in front of u. So that's going to be equal to e to the 5 natural log of x, which we know is just going to be equal to x to the power of 5. So multiplying both sides by x to the power of 5, we're going to get x to the 5 u prime plus 5x to the fourth u, and that's going to be equal to 3x to the power of 3. So we have this particular equation, which you should recognize as just a backwards product rule. So we can write that as the derivative of x to the fifth times u, and that's going to be equal to 3x cubed. We can multiply both sides of this equation by a differential of x and then integrate. So we're going to have that x5u is going to be equal to 3/4 x to the power of 4 plus some arbitrary constant c. Okay, so once we get that, keep in mind we can solve for u in this case. So we can say that this is going to be u is equal to 3/4 times 1 over x plus 1 over x to the power of 5 times our arbitrary constant c. And keep in mind that u is just a fancy way of saying y prime. So again, we have a first order differential equation, but moreover, on the left-hand side, we just have some function of x. Therefore, we can just simply integrate this particular differential equation and get our solution y. So if that is the case, what are we going to have? Well, keep in mind we do have a particular, actually let's just go for y. So y is going to be equal to, actually no, let's get this constant c from the start, just so that we don't have two constants hanging around a little bit later. So we know that x is equal to, when x is equal to 1, y prime is equal to 1, so we should be able to solve this equation for c. So when we have that, what are we going to have? So we're going to, I think maybe using this equation with y prime in the place of u is probably the safest move here. So we're going to have 1 on the left-hand side, that's going to be equal to 3/4 times 1 plus c, which means that c is just going to be equal to 1 minus 3/4, which is just going to be equal to 1/4. So we can just substitute that in and then move forward. So we have y prime is equal to 3/4 times 1 over x, and then over here we have plus 1/4 times 1 over x to the power of 5, right? Which we can also write as 3/4 x to the minus 1, then 1/4 x to the minus 5. Right? So once we have this particular equation in terms of y prime, then we just integrate with respect to x to get y. And then, of course, we're going to get another constant, of course. So we're going to have y is equal to 3/4. The antiderivative of 1 over x, as we know, is the natural log of the absolute value of x. And then over here, when we add 1 to that particular power, we're going to have -4. Divide that by -4 to get -1/16 as my constant, and then x to the minus 4. And then we're going to have some new arbitrary constant, so you can call it c2 if you don't want to use the same constant over and over again, but that's going to give us that particular thing. So, from our other initial condition, when x is equal to 1, we know that y was equal to 1 over 32. So using this criteria, we should be able to get what c2 is equal to. So that's going to give us what? 1 over 32 is going to be equal to 3/4 times the natural log of 1, which we know is going to be equal to 0, and then minus 1 over 16 times 1 to the power of minus 4, plus our constant c2, which we're going to look for. So this piece is going to disappear, and then we're going to have that c2 is going to be equal to 1 over 32 plus 1 over 16, and then we can multiply top and bottom of this by 2, and we're going to have 3 divided by 32 as our constant c. Right, so let's sort of review what we have here. So we had y double prime plus 5 over x y prime is equal to 3 divided by x squared with the initial conditions. Y of 1 was equal to 1 over 32, and y prime of 1 was equal to 1, and we have found that our particular solution, which I'm just going to call yp, is going to be equal to 3/4 times the natural log of x minus 1/16 x to the power of minus 4 plus 3 divided by 32. And that is our solution to this second order differential equation, which of course we didn't really have to learn anything new to solve that. We just introduced substitution and we were able to solve it. But the only reason that we were able to solve it was because we had y double prime and y prime and we didn't have the y term. So let's look at a few other things that we definitely should know in the general sense. One important principle that you definitely need to know when working with a lot of the basic classes of higher order ODEs, for example, is that if you know one solution, either by observation or maybe guessing or trial and error, if you can find one solution, you might be able to determine one or infinitely many more solutions that might be related to the solution that you know. So if we take, for example, the differential equation y double prime plus 7y prime plus 10y is equal to 0, this is a very basic example of a second order linear constant coefficient homogeneous differential equation. And when I say constant coefficient, the things in front of our y double prime, y prime, and y are just constants. They're not functions of x. And also, it's set equal to 0, making it a homogeneous second order differential equation. So, one thing I leave to you is just an exercise because it's actually not hard to prove, is that y1, which is given by e to the minus 5x, and y2, which is given by e to the minus 2x, are both solutions. Right? So if you take the second derivative, first derivative, and their original forms and plug them each into this equation, you will get 0 for that particular linear combination. And also another exercise that is also fun to try is that y1 is equal to c1 e to the minus 5x and y2 equals c2 e to the minus 2x, where C1 and C2 are any real numbers, are also solutions to this equation, right? So in some sense we have two little families of solutions, in some sense both exponential decay, but they need not be decay for the general case. But any scalar multiples of those exponential decay functions are going to be solutions to this differential equation, which begs the question, are there other families of solutions for this? Are there other families of solutions? And what do I mean by families? So if we define a set S of all the families of functions, in particular in this case e to the minus 5x and e to the minus 2x, and scalar multiples, are there any other functions that make this equation true? For example, if you try e to the minus 3x, will it work? Well, if you try sine of 2x, will it work? If you try x squared, will it work? Well, if you add these two functions, e to the minus 5x and e to the minus 2x, will they work? Right? So, how many solutions do you think there truly is for this particular second order differential equation? So, one question that I do want to answer is the following. What about the sum of these equations? So when I say the sum, I mean y is equal to e to the minus 5x plus e to the minus 2x. Is this a solution to this differential equation? Yes or no? So what I want to do is I actually want to verify that this actually is a solution. So the individual ones are not hard to prove, but the sum of them also is going to work as well. So if we take the first derivative of this, that's going to give us minus 5 e to the minus 5x. So minus 5 e to the minus 5x, and then minus 2 e to the minus 2x. And then the second derivative is going to be equal to 25 e to the minus 5x, and positive 4 e to the minus 2x. And then we're going to plug these four statements into our differential equation. So we're going to have y double prime plus 7y prime plus 10y. And our question is, are they equal to 0? If they are, then it is a solution. So y double prime is going to be 25 e to the minus 5x plus 4 e to the minus 2x, and then plus 7 times y prime, which is minus 5 e to the minus 5x, and then minus 2 e to the minus 2x, and then plus 10y, which is 10 e to the minus 5x plus e to the minus 2x, and let's see what this is equal to. So what I want to do is I want to group my e to the minus 5x terms together. That's going to give me 25, so 7 times minus 5, that's going to be minus 35, and then plus 10 e to the minus 5x, And then we're going to be grouping our e to the minus 2x terms together. So that's going to be plus 4, 7 times minus 2 is minus 14, and then plus 10 e to the minus 2x. So those constants added together is going to be 0 e to the minus 5x, and then plus 0 e to the minus 2x, which is going to be equal to 0 for all values x in the associated domain. So it gives us 0, which is the right-hand side of that second order differential equation. Therefore, y is equal to e to the minus 5x plus e to the minus 2x also is a solution. Right? So that's pretty interesting. So e to the minus 5x works, e to the minus 2x works, scalar multiples of the individual exponentials also work, and the sum of the original two exponentials also work. So another fun little exercise for you is to prove the following, that y is equal to c1 e to the minus 5x plus c2 e to the minus 2x also is the solution. Also is a solution. And with some more theory, which we'll definitely build in the future, this is actually the general solution to this differential equation. That means any solution to this differential equation can be represented as a linear combination of these two things, right? So if you know anything about linear algebra and linear combinations and independent vectors, we can say, okay, well, if we have s is equal to e to the minus 5x and e to the minus 2x, which you can, in some sense, think about as vector functions. For example, we can call this vector 1 and vector 2, or more so, vector y1 and vector y2. All solutions of our ODE can be represented as linear combinations of y1 and y2. Which means if you have any y that satisfy that, that means y can be represented as c1y1 plus c2y2. If you did take linear algebra in the past, you might need to show that, for example, y1 and y2 are independent vectors. But what does that mean in terms of independent functions or independent solutions? We'll get to that a little bit later, but this is actually something interesting to think about while we're beginning our journey through higher order differential equations. Now, there's a couple important things that I want to mention about these constant coefficient linear higher order differential equations. In particular, the next point that I want to make is just a review of an important part from differential calculus. If you take the nth derivative of an exponential function with a rate parameter lambda, one can find that that's just going to be equal to lambda n e to the lambda x. Therefore, differentiation just scales exponential functions. Right? So differentiation of exponential functions scales the exponential function. So the more and more you differentiate an exponential function, the more and more it scales it by whatever the factor of the rate parameter is going to be. So with this, if we define y to be equal to a sum of exponential functions, let's say the sum from k is equal to 1 to, let's say, m of ak e to the bkx, where ak and bk are just sequences of real numbers from k is equal to 1 to m, then the nth derivative with respect to x of this function y is just going to be what? So that's just going to be equal to the derivative with respect to x n times of this thing, and that's just going to be equal to, again, the sum from k is equal to 1 to m of ak bk to the power of n times e to the bkx, right? So if you sort of look at this, well, that's just another sequence of real numbers, right? So we can, for example, call that a sequence ck. So it's just the sum from k is equal to 1 to m of ck e to the bkx. Again, it just changes the scalar factor in front of those exponential functions. But if you look overall at the type of function we're dealing with, it practically has the same exact structure. It's just scaled versions of exponentials with actually the same exact rate parameters that they used to have. So if we take any combination of derivatives of exponential functions, they still are going to be an exponential function. Therefore, if you have, for example, some constants in front of these things, for example, if you have 5e to the x or 5e to the 5x minus the derivative of e to the 5x, you're going to be like, okay, well, that actually makes sense because notice that this is our y and this is sort of like our y prime. So it's like y prime minus the derivative of some y. That, of course, is going to be 0. So if I have the differential equation, let's use the same one as before, y double prime plus 7y prime plus 10y is equal to 0. And you're like, okay, well, what type of function would y be? Is y a polynomial? Is y a trigonometric function? Is y an exponential function? Well, if y is an exponential function and we sort of combine any linear combination of exponential functions with its derivatives together, it definitely is possible to get 0 as long as those rate parameters in our solutions are, satisfy some algebraic relation. So we're like, okay, well, if y can be represented as an exponential function where lambda is some rate parameter for which we don't know yet, then what we're going to have is y prime is just going to be equal to lambda e to the lambda x, and y double prime is just going to be equal to lambda squared e to the lambda x. So if we substitute these three expressions into this differential equation, and we're like, okay, if y has this form, what values of lambda would this need to be in order for it to truly be a solution of this differential equation? So once we substitute, that's going to give us lambda squared e to the lambda x plus 7 lambda e to the lambda x plus 10 e to the lambda x, and that's going to be equal to 0. So keep in mind, e to the lambda x is never going to be equal to 0, and that's going to be true for all x in the set of real numbers. It's either always going to be exponential decay or exponential growth. So we can divide both sides of this expression by e to the x, and that's going to cancel our exponentials, and 0 divided by an exponential is going to be equal to 0 as well. So what we have here is lambda squared plus 7 lambda plus 10 is equal to 0, which is just a quadratic equation in terms of lambda, which we should be able to solve. Because we're like, okay, what two numbers multiply together to give us 10 and adds together to give us 7? And we're like, okay, that's just going to be lambda plus 5 and lambda plus 2 is equal to 0, giving us two values of lambda, in particular minus 5 and minus 2. So we're like, okay, that's cool. Well, that means that our solutions, for example, y1 would be equal to e to the minus 5x, and y2 would be e to the minus 2x. Right? So if y is an exponential function, then these two would have to work, and there's some algebraic justifications to that. And we've already verified, or one could verify for the general sense, that if y1 is the solution to this particular type of structure, in particular y double prime plus ay prime plus by is equal to 0, where a and b are both constants, in particular real valued constants in this case, then if y1 and y2 are individual solutions, scalar multiples of them will also work, and also their linear combinations will also work as well. Therefore, with those justifications behind us, the general solution would be equal to c1 e to the minus 5x plus c2 e to the minus 2x, and that will give us our general solution for that constant coefficient differential equation. Now that we have some exploratory wisdom behind us, let's look at a third order differential equation and see if we can solve it. Notice again that we have a constant coefficient, third order, homogeneous differential equation. So one can show that if you can find a solution y1, y2, and y3 that are in some sense significantly different from each other, their linear combinations will also be a solution, and further theory can prove that that is actually the general solution to this differential equation. Since it's constant coefficient, a good guess for the true solutions, the individual solutions for y1, 2, and 3 are probably going to be exponential functions because we know their linear combinations can be equal to 0, provided that the right parameters are sufficient. So let's assume that our individual y's are of the form e to lambda x. Let's figure out what those lambdas are. So using the third, second, and first derivative and then dividing both sides by e to lambda x, you're going to find that this is going to give us the cubic equation lambda cubed plus lambda squared plus 6 lambda is equal to 0. So we clearly see that we have a greatest common factor of lambda, which is actually pretty nice. So that's going to give us lambda times lambda squared plus lambda minus 6 is equal to 0. And that's a nice factorable quadratic. So what two numbers multiply together to give us negative 6 and add together to give us positive 1? That's going to give us positive 3 and minus 2. So we have three values of lambda here. In particular, we have lambda is equal to 0, minus 3, and positive 2. So once we have that, then we can say that the general solution, which I'm going to abbreviate by YG, is going to be C1 e to the minus 3x plus C2 e to the 2x. And then over here we have C3 e to the 0x, which is just some constant. So you could also write it as YG is equal to C1 e to the minus 3x plus C2 e to the 2x plus some constant C3, and that would be your general solution to that first differential equation. So how would you get a particular solution for this? So if we want a particular solution, then we need to have some values for which our original function y satisfies. So one can show that in order to have a particular solution, you need three criteria. In particular, since we have three unknowns, C1, C2, and C3, we need three known things about it. So let's assume that we know that y of 0 is equal to 5, y prime of 0 is equal to minus 3, and y double prime of 0 is equal to 2. So these are going to be our three initial conditions. Once you plug all three of these three things into our equation above, right? So this is your y value, and you can plug in our 0 values, differentiate it 1 and 2 times to get these relations. You're going to get the following systems of equations. So for example, y0 is equal to 5 is going to give us 5 is equal to e to the 0 is 1, so we're going to have c1 plus c2 plus c3. When we differentiate it, that minus 3 and 2 are going to come downstairs. So we're going to have minus 3 is equal to minus 3c1 plus 2c2. c3 differentiates to 0. And then we're going to differentiate again. And that's going to give us 2 is equal to 9c1 minus 3 squared, and 2 squared is going to be equal to 4. So we have a system of 3 by 3 systems of linear equations. So you can write that in matrix form, so you can perform some Gauss-Jordan elimination if you want to. So we have 1, 1, 1, minus 3, 2, 0, and 9, 4, 0, with our constants C1, C2, and C3, and those are all going to be equal to 5, minus 3, and 2. So in matrix form, we can write this as AC is equal to B, where C and B are vectors and A is our coefficient matrix, and therefore we can see that C is just going to be equal to the inverse of A times the vector B. Right? And there's plenty of linear algebra things there. So one can say, well, is this solution going to be unique? Well, we hope so, but we can find that the determinant of this coefficient matrix is equal to minus 30, which is not equal to 0, which means that C exists and is unique. So there is a unique solution with these three initial conditions. So once you do perform that Gauss-Jordan elimination, which I will not go through here, that's just going to give us 8 over 15 minus 7 over 10 minus 7 over 10 and 31 over 6. So that is going to be my solution. And if you're not sure why I'm putting the t there, that's just a transposition because it should be a column vector, not a row vector, but I just want to save some space and write it as a row vector instead. So once you have your constants from your initial conditions, that means we're going to have a particular solution to our differential equation, and that's going to give us 8 over 15 e to minus 3x minus 7 over 10 e to the positive 2x plus our lonely little constant at the end, 31 over 6. And that's going to give us our particular solution for our third order constant coefficient homogeneous differential equation. I want to close out this video with just a couple examples, but the solutions to these differential equations you definitely probably should already know, but we're just going to solve these equations via this new insight that we've already discussed. So let's consider the differential equation y prime is equal to y with the initial condition of y0 is equal to 1. You should be able to immediately tell me what the solution of this differential equation is, because it's such a popular function in terms of single and multivariable calculus. So you can be like, okay, well, this is a separable differential equation. I can solve it via that way, but actually let's write it as y prime minus y is equal to 0. because that's just a linear combination of potentially exponential functions. So we're like, okay, if y is equal to e to the lambda x, then we're going to have lambda minus 1 is equal to 0. And we know how to solve this equation, so that's going to be lambda is equal to 1. So that means the general solution is going to be equal to c e to the x, right? So that's my general solution. And we're like, okay, we have this initial condition where y of 0 is equal to 1. So we're like, okay, well, 1 is going to be equal to c times 1, which means c is equal to 1. Therefore, the particular solution to this differential equation is just our favorite e to the x. So if someone were to ask you, what is this function f of x is equal to e to the x? What is so special about it? You can answer with the following. It is the unique solution to the ODE, or initial value problem, y prime is equal to y with y0 is equal to 1. Right? And as long as you have some physical meaning and importance for this particular initial value problem, i.e. the derivative of something is itself, and it must pass through the y-axis at y is equal to 1, then you're like, okay, whatever function that is, I'm going to give it a name, and its name is going to be e to the x. So we can see, okay, well, if we don't know the true solution to this differential equation and we have some meaning for that differential equation, we can start defining new functions as the solutions for these differential equations, which is going to be very, very important for several of these higher order differential equations that we will explore in the near future. So let's consider another one, in particular y double prime plus y is equal to 0. So second order constant coefficient. Let's consider these two initial conditions. Y is 0 is equal to 1 and y prime of 0 is equal to 0. You might be able to eyeball the solution to this, but let's pretend that you do not. So obviously, linear combination of exponentials would be a good guess. So if we let y be equal to e to the lambda x, that's going to give us lambda squared plus 1 is equal to 0. So that's just the sum of perfect squares, so we can factor over the complex numbers with no issue. We're going to have lambda plus I and lambda minus I is equal to 0, giving us two values for lambda, I and minus I. So that's going to give us our general solution to this differential equation, at least over the complex numbers. So we're going to have our general solution is going to be equal to c1e to the ix plus c2e to the minus ix. Okay, now we can use our initial conditions. So if we have y0 is equal to 1, we're going to have 1 is equal to c1 plus c2. And if we use our second initial condition, y prime of 0 is equal to 0, that's going to give us 0 is equal to I times c1 minus I times c2. So we have a nice little system with two equations, two unknowns, in terms of c1 and c2. If we write this as a matrix equation, that's going to give us 1, 1, I minus I times C1, C2 is equal to 1, 0. And that equation actually isn't too bad to solve. You can multiply the first equation by I and then add the equations, for example, to eliminate your C2 equation. But regardless of how you solve it, one can find that C1 and C2 are both going to be equal to 1/2. Nice numbers actually, right? So once we have that, then we have that our particular solution is going to be equal to e to the ix plus e to the minus ix, both of them over 2. So that is our particular solution. So you're like, okay, well that looks like a very strange function, but if you have studied some exponential transformations on Taylor series for functions that are important, you might recognize this function already, because using the Taylor series of sine, cosine, and e, you should be able to find that this is just another way of saying cosine, right? So notice that we were able to derive the exponential complex representation of cosine via just this guess of, maybe our functions are just exponentials in disguise. But you should be able to verify just from the derivatives of sine and cosine that cosine actually is a solution to this equation as well. And you could guess, well, is there any relationship to these things? How can you be so sure that these two things are equal to each other? Well, one can show that if you have a set of two functions, in this case e to the ix and e to the minus ix, and they are what we call independent functions, then those are the only solutions to that constant coefficient homogeneous differential equation. And since yp is equal to cosine, that means cosine must be able to be represented as this representation or subset or superset thereof, but you should be able to verify with Taylor series that they actually are equal to each other. So if somebody asks you, what is cosine? You can say, well, cosine is just the solution of the differential equation y double prime plus y is equal to 0, with initial conditions y is 0 is equal to 1, and y prime of 0 is equal to 0. So it's just an introduction to higher order differential equations. Lots of interesting problems and differential equations to explore and their solution methods, but we'll get there eventually. Hope you enjoyed this video, and I'll see you in the next one. Take care.